So in this class we are going to discuss about different thermodynamic processes. Depending on how the process happens, we have different kind of thermodynamic processes. Whether the process happens at constant temperature, at constant pressure, or if there is no energy transfer between system and surrounding. Likewise, based on certain conditions, we call some process thermodynamic processes with certain names. One is quasi-static process. Quasi means partially, not completely, almost in the sense. Like almost static process. Static means stationary. There is stationary in the sense here means there is no much change in the state of the system. The condition for this process is it should be a slow process. The process should be very slow so that every time the system is almost in the same state compared to the previous state. That is, there is no drastic change in the conditions of the system will be almost in equilibrium in all the small intervals. It's actually not a real process, it's an assumption type process. Like I can say it's an idealized process, idealized condition. It's not practically possible 100%. Another one process we have to see is isothermal process, which you know already. Iso means same, thermal comes like a temperature, related to temperature. So it's a process that happens at a particular constant temperature. So throughout the process temperature will be same in the system. Such a process is called a isothermal process. We represent the isothermal process by the help of an equation, that is PV is a constant. P into V is equal to a constant. Pressure into volume is a constant. How that comes is we have an equation for PV is equal to nRT, where n is the number of moles of the particles and R is gas constant, T is the temperature. So if N and R are constants already, if T is constant, this term PV is a constant. That's how we get the equation PV is a constant. Now, in such a process, in such an isothermal process, we need to know what is the work done in this case. So let us consider the equation for the work done. In the case of a system, let the system be gaseous system, and that gaseous system has a initial temperature, pressure, and a volume. And during this process, the temperature is remaining constant, we told. That means T in temperature there is no change, but the pressure and volume can be changed. So system may be initially at a pressure P1, its volume can be V1, but finally its pressure becomes P2, volume becomes V2. Now this process, let's take a small change in the volume, that is delta V, a change in the volume. Then the work done during that process, we know it is P into delta V. We have already got this expression like P delta V as the work done, small work done. To get the total work done, we integrate this. That is integral P delta V or P dV. Both are same. This symbol or this symbol I can use P dV. This is more a better term, dV. And the limit of this integration we have told already. The work done W is equal to integral adding all the small work done from V1 to V2, and that is integral P dV from V1 to V2. If you integrate this, we get P into V, and the variable is from V1 to V2. Now one more thing before doing that, this equation let's consider, that is the ideal gas equation, PV is equal to nRT, and from that let's write the pressure P is equal to nRT by V. This is one possibility, P equal to nRT by V. Before integration itself we can substitute this here, replace this P with nRT by V. Integral is there, V1 to V2, and this is dV. Now this comes like nr and T is constant for an isothermal process. So this integration is applicable from for V1 to V2 1 by V dV, 1 by V dV. If you integrate it from 1 by V to dV, 1 by V dV, if you integrate this, what we get is log nRT, natural logarithm ln V from V1 to V2. This log ln is not our usual log, but you can write it in usual log by adding a number 2.303. If I write like this 2.303, it becomes the usual logarithm you are using. Now I can write it as log V log V, but this is varying from V1 to V2. Another one things which we need to know is 2.303 nRT. Here, after getting this value V, log V, I should write it as, first I should give the upper limit V as V2 minus log lower limit V1. This is in the form log A minus log B, but log A minus log B is log A by B. So I get 2.303 nRT log V2 by V1. This is how I can get the expression for the work done in the case of an isothermal process. So W is 2.303 log 2.303 nRT log V2 by V1. So this is the expression for the work done in such an isothermal process. So two processes we have seen so far, that is quasi-static process and isothermal process. Another one process which we have to study is about adiabatic process. An adiabatic process means a process in which there is no heat exchange. That means we have a system, and during this process there will be a system and surrounding. During this process no heat goes out from the system and no heat comes into the system. That is, the system is made up of adiabatic wall, non-conducting wall, so that there is no heat exchange between system and surrounding. That process is called an adiabatic process. So here, as there is no heat exchange, the heat Q we can write as 0. Q is equal to 0. So we can make some walls of the system by using the materials like cork, asbestos, etc., which does not allow the heat to flow. So such a kind of system which we give a surrounding with the help of this kind of material, heat exchange will not happen. Then there is no heat exchange between the system and the surrounding. Process is adiabatic. Now for such a process, let's take the first law of thermodynamics, which we said, which is equal, which will state like delta Q, the heat, is equal to internal energy change plus the work done. This let's consider. For an adiabatic process, delta Q is equal to 0, which means 0 is equal to delta U plus delta W, which is the delta U is equal to minus delta W. This is an equation which we can give for an adiabatic process. That's what written here, delta U, which is U2 minus U1, final internal energy minus initial internal energy as minus delta W. So this is one equation representing such a adiabatic process. Now let's see what's the relation between P and V, pressure and volume, for such an adiabatic process. So we'll go back to the same idea, first law of thermodynamics, that is a delta Q or dQ. D or delta, I can use it interchangeable. Both are same. dQ is equal to du plus dW. This is coming from the idea heat given is used for two purposes. One is for changing internal energy, other one for doing the work. Now for an adiabatic process we told dq is 0. dw already we have work done, that is p delta v or p dv. And let's take for this kind of adiabatic process, let's see how is the energy relation comes. Let's go back to the first law of thermodynamics once again, which says delta q is equal to delta u plus delta w, or dq I can write as dq is equal to du plus dw. Divide this equation with a dt, the temperature dt is equal to du by dt plus dw, which is p dv. We told p dw is work done is, what is that, yeah, work done is p dv. We have already here dw is p dv, so p dv by dt. Now if I consider this r at constant volume, this term becomes 0, then I get du by dt at constant volume is equal to dq by dt at constant volume. This dq by dt is at constant volume is nothing but cv. This is cv. So cv is du by dt at constant volume. So that's what written here. Du, I can write cv is equal to du by dt. This is at constant volume. So du is equal to cv dt. I can write like this. du is equal to cv dt. This is what I have. So instead of this equation here, I have dq is equal to du plus dw. This equation becomes dq is 0. 0 is equal to du is cv dt plus dw, that is pdv. So this is how I get this equation. 0 is equal to cv dt plus pdv. Once again, from ideal gas equation I take PV is equal to RT. For 1 mole N is 1. So if I differentiate both sides, I get a PdV plus VdP is equal to RdT, and from that I can take dt is equal to PV plus VdP by R. So little lengthier derivation. So from this PV is equal to RT, I take P, I just take the differentiation on either side. So this is product rule, P into V. So first one P into differential of the second dV plus second one V into differential of the first one dP is equal to R into dt. So from this dt I take R to the left side, R comes in the denominator. Now look at this equation, cv dt, 0 is equal to cv dt plus pdv. In this dt I substitute this full equation. This dt, instead of this dt I substitute this. So cv into dt means pdv plus vdp by R plus pdv is equal to 0. Just open this bracket, cv into pdv, cv into vdp, and multiply this equation with R. Just you can multiply from this. First you multiply with this equation completely with R. This equation fully you multiply with R. Just multiply. Then this cancel. This denominator R will cancel. Here one extra R will come. That R is here. Open this bracket, CV PdV plus CV VdP plus RP dV is equal to 0. Now PdV is in two terms. One is PdV here, and another one is again PdV here. So these two terms we can take together, Cv plus R. That's what here, Cv plus R into PdV plus this term Cv VdP. Now I get Cv VdP plus Cv plus R PdV is equal to 0. But we know Cp minus Cv is equal to R. So Cv plus R is nothing but Cp. So I get Cp here. This is Cp. Cv VdP plus Cp PdV is equal to 0. If I divide this completely with Cv PV, Cv into PV, Cv and PV, if I use and divide this completely, I get like this, Cp dP by P plus Cp by Cv into dV by V is equal to 0. Just try to write down like this. If you try yourself, you will get this equation. So dP by P plus Cp by Cv is there. Cp by Cv is gamma into dV by V is equal to 0. Now this you get you can integrate this. Once you integrate this, 1 by P dP will come, that is log P. Gamma 1 by V dV, this if you integrate you get log V. So this will give log P plus gamma log V is equal to C, can be written as log P plus log V to the power gamma is a constant. Because you integrate 0, you get a constant. So PV to the power gamma is a constant. That is what the equation for an adiabatic process. The expression for the adiabatic process. Similarly, we can find the expression for work done in adiabatic process. This is just an equation representing the adiabatic process. We can do the you can find the work done in adiabatic process. You can go ahead with this. It's not compulsory to know the derivation part because it's an integration derivation. All the integration derivations CBSE has told, like you can skip the integration steps and all, you can focus only on the equations. So the work done, no need to derive it completely. The work done for an adiabatic process is nR by gamma minus 1, where gamma is Cp by Cv, R is gas constant, N is the number of moles present, T1 minus T2. That's the difference in the temperature. So just take this equation alone, that is fine. Another two processes which you need to know is, one is isochoric process, in which the volume of the gas or the system remains unchanged throughout the process. So there will be no change in the volume of the system. So when volume is 0, work done is also 0, because work done is delta W is P delta V. So when volume is constant, volume change is 0, work done is 0, which means delta U is equal to delta Q. This is an equation for isochoric process. Another one process is isobaric process, in which pressure is remaining constant. So this process happens at a constant of pressure, nothing more. So in this case, the pressure is kept constant throughout the process. So for an isobaric process, let's write the work done. Work done is actually P delta V, that is P into change in volume V2 minus V1. But PV is nRT. So in that case, P V2 minus V1 should be equal to nR T2 minus T1. This is also an equation for the isobaric process. P into V2 minus V1. This is the work done in this case. W is equal to P into V2 minus V1 equal to nR into T2 minus T1. So these are the different thermodynamic processes involved.